Hello everyone, I am Miss Hu, your physics teacher. In this video, we'll be going through the concept of center of gravity. What we'll be covering in this video lesson are, we will learn to identify the position of the center of gravity, describe how the center of gravity affects stability, as well as predict whether an object will fall when tilted. So, first things first, we need to know what the center of gravity is, as in what it means. The center of gravity is the point from which all of the weight of the object seems to act. In most cases, it is the same position as center of mass. Now, center of gravity and center of mass are two different things. They do have their own definitions. In this video, I'm not covering center of mass. So if you want to know more, I'll cover that in another video. We will focus on center of gravity for this lesson. In most shapes, provided that the object is uniformly distributed in terms of its weight, you'll find that the center of gravity tends to be where the center of the object is. So, for example, if we look at these three shapes, and let's say we cut out these shapes from pieces of cardboard, so they're all in 2D. One of the things you'd have learned in maths is to find the center of these polygons. So, for example, for the triangle, if you drew a line from one of the vertex to the middle of the opposing side, and you do the same for all three vertices, you'll find that they all intersect, and that's where the center of this 2D shape is. And if you were to cut out this triangle from a piece of cardboard, you would find that the center of this triangle is equivalent to the center of gravity of this shape. This also applies for the circle and even for a polygon like this shape. So if you'd like to prove that those are the center of gravities, you can actually do an experiment with a piece of 2D lamina. If you'd like to do the experiment, I do have a video where I show step by step how to determine the center of gravity for 2D shapes. And I've put the link in the description below. Now, all I've mentioned just now is just the center of the object. How does that center make it the center of gravity? Now, we know that for objects, of course, the weight is distributed throughout the entire object. However, you'll find that for all objects, they seem to have an interesting way of interacting with gravity. The weight seems to act from one point. So if you do the experiment to find the center of gravity, to try to prove that that's the center of gravity, you'll find that the center of gravity is where you can balance that object on a point. So for example, if I have a pen like this. Now, as you can see, of course, the pen has material throughout. And yes, there's weight distributed throughout the entire object. And I'm sure you've done this before. If you try to balance the pen on a particular point, you'll find, hey, it can balance. Any other point will cause it to topple, so it's not so stable. Now, if we can balance the pen on a single point, why this can happen is because actually the weight of the pen is acting from this point, and my finger is right now supporting the position of where the weight seems to act. Because there's gravitational force pulling the object down and it seems to act from a point, normally you'll find that it acts only at a certain point. And if I were to draw an arrow from the center downwards, this arrow here represents the force of weight of this object caused by gravity. So in all objects, you'll find that yes, the weight seems to act from a particular point. Whoops, imagine it straight. The weight seems to act from a particular point on that object, and that point is known as the center of gravity. It's where the weight seems to act from that point in that object due to the force of gravity. Just to make sure that you understand the labels here, I'm going to label this as W, so that's the weight. So these are the weight lines of the respective shapes. The center of gravity are the points which are marking in green in these respective shapes. So these points are the center of gravity. One thing you got to understand about center of gravity is that it is not the point from where the weight of the objects are acting, it's the point from which all of the weight of the object seems to act, the point where the weight of the object appears to act. So it's not that that's where the weight is, it's the point where the weight seems to be focused at, and the way that the object interacts with the force of gravity to create weight There's a point of interaction, and that's the center of gravity. Just to make it clear. So for 2D shapes, they're quite easy to observe. What if the shapes are in 3D? For 3D objects, the center of gravity still is the point from which all of the weight of the object seems to act. And for 3D objects, the center of gravity is inside the object, not on the surface, but inside. So say for example, if I have a mouse like this, it's a 3D object. The center of gravity is not on the surface, rather it's inside. So I cannot point to you exactly where the center of gravity is because my finger cannot access it. It's inside the object. Now, is it possible for the center of gravity to be outside the object? Well, kind of. So say we have an example like this. Whether it's 2D or 3D, it's possible for the center of gravity to be outside the object. The center of gravity is not technically outside the object, but rather at a zone where there's no material for the center to be acting from. On the left, we have a 2D donut, and on the right, an image of a 3D donut. In both cases, the center of gravity is in the middle. So let's look at the 2D donut for clearer visualization. And you see that the hole is also another perfect circle. We know that for a circle, the center of gravity is the center of the circle. So if both the external and internal circles happen to share the same center, when you've cut this out, it doesn't affect where the center of gravity would be, which means that the center of gravity would still be where the center of the circles are. As you can see, the center of gravity over here is where the hole is. Now, can you prove this with a piece of 2D card? It is very difficult because it's a hole. There's no place for you to try to balance with your finger. But if you can answer that, yes, this is the center of the external circle. And if you were to cut out a circle that shares the same center, that doesn't change the position of the center of gravity. So technically, yes, the center of gravity can be found at a position outside the object, meaning where there's no material from which the center of gravity can act from. If you can understand this for a 2D object, the same applies also for a 3D object, which means that for this 3D donut, the center of gravity is where the donut hole is. Now, what we've been covering so far are the center of gravity for objects that have the weight uniformly distributed. What we mean by uniformly distributed is that throughout the entire object, the material is probably the same, or that the weight distribution is the same. That means that the weight throughout the entire object, like the donut for example, the material is the same throughout. If you were to have composite objects where we combine objects made of different materials or densities, obviously the center of gravity would shift. Say for example in this diagram, yellow and green represent two different materials with different densities. Now obviously when we combine them, the center of gravity is going to shift. Let's say in this example, green color has a greater density. If we were to look at the individual center of gravities for the objects, for the yellow object, it would be roughly about here, whereas for the green color object, it will be around here. But when you combine the objects, they now act as a single object. So you cannot have one object with two different center of gravities. So what's going to happen is both of them will combine to form an object with one single center of gravity. And the center of gravity tends to shift towards the area where there's greater weight. So if let's say in this example, the green color object has greater density, that means there's a greater weight concentration on the right side. Obviously it's heavier on the right side. So let's say for example for this pen, if let's say this material was higher density and this material was lower density, you'll find that the weight tends to be more on the right side. That's why the balance is more on the right side where the higher density material is. That means it is possible, for example, the new center of gravity would be over here. Just because you combine two different materials doesn't always mean that the center of gravity will be exactly at the same point. It does depend on the weights of the respective areas. So if we use the same two densities but the materials are of different volumes, then obviously the weights will be different as well. So it's possible maybe the center of gravity would be on the side of the yellow instead, but still quite close to the area where there's greater density. So it does depend on the object. So if you wanted to find the position of the center of gravity, you can always try to find a balancing point. And because gravity always pulls downwards, the vertical line from that balancing point is roughly where the center of gravity would be. Now that we understand center of gravity, we have to understand a little bit more about toppling. So when we talk about toppling, we must first understand what factors affect stability. So when we talk about stability, that means that if we were to try to push the object, which object is more likely to fall over? The harder it is to try to get the object to fall over, the more stable the object would be. So to understand stability, let's look at these two pairs of triangles. So on the left side here, you can see that both triangles have the same height, but one has a greater base area than another. So I want you to think, if you were to try to push these triangles over, which one is more likely to fall over? The one with the smaller area, right? And yes, that's because that's one of the factors. So the factor that we're looking at here on the left pair is the base area. So the greater the base area, the more stable the object. Now, if you were to look at the right pair, you'll find that both of them now have the same base area. One has a greater height compared to the other. And again, I want you to think, if you were to try to push these triangles over, which one is more likely to fall over? Interestingly, the taller one, right? Try to think, if you have a short little cup and a tall cup with the same area you push over, it's harder to knock the shorter one over. And in this case, it is not so much the height, but rather the position of the center of gravity. So it's not the height of the object, but rather height of the center of gravity. The lower the center of gravity, the more stable the object. So if we compare these two, it so happens that yes, because this triangle has a greater height, it will also have a greater center of gravity. So in the case of the shorter triangle, the center of gravity would be about here, whereas for the taller one, if you were to try to find it, it would be here. So that's why it is less stable. Now, why is it that the base area and the height of the center of gravity can affect the stability? Let's look at it more closely in terms of toppling, but before we go into that, let's just have a quick understanding about the different types of stability. Generally, you need to know there are three types of stability. We have stable equilibrium, unstable equilibrium, and neutral equilibrium. What do these all mean? Stable equilibrium is a situation where if you push the object so that it becomes unstable, you'll find that it will come back to its original base. That means this situation provides stable equilibrium for this object. So for example, this triangle, this is the base where it's resting on. When you push it, it will come back to this base. So this situation provides stable equilibrium for this object. We also have unstable equilibrium. Now let's say you're one of those who's amazing at trying to balance an object directly over its center of gravity. So if you could get this cone, for example, to balance on this tippy edge here, and wow, it's able to remain upright, that's amazing. I can't do that. I know some people who can. This is considered unstable equilibrium. Why? Because if you were to nudge or push this object so that the center of gravity shifts, then it will fall over and it doesn't come back to its original situation. That means that at this point, it is unstable equilibrium because it's easy to make it topple over and become unstable. Neutral equilibrium, on the other hand, is a situation where it remains stable throughout. So for example, this sphere. Right now you can see it's balanced. If you were to push it, it doesn't go back to its original position, nor does it topple over. It just continues to remain upright and stable. That means throughout the entire situation, when we push this sphere, it remains stable. So that's neutral equilibrium. Now let's have a closer look at how the base area and the height of center of gravity affects the stability and toppling of an object. Now, if you were to tilt an object, it will topple, meaning will fall over, when the line of gravity is outside the base of support. So let's look at the first diagram over here. Now let's say this black arrow here represents the weight, and we draw the weight line from the center of gravity downwards. So that's what we mean by the line of gravity. So the line of gravity is a line that goes through the center of gravity vertically. The base of support that we're referring to here is the surface where the object is resting on the ground. Now, if we were to tilt the object, there are two possible situations. Either it's going to remain, or it's going to come back to the stable equilibrium position. That means it goes back to the original base, or it's going to fall over. But how do we know whether it's going to come back to its original surface or is it going to topple over? It depends on where the line of gravity is relative to the base of support. So we have different positions of tilting here. Let's compare the weight against the base of support. So I'm going to draw weight lines for each object. Let's have the second diagram first. So I've shifted it here. If this is the center of gravity and this is where the weight line is, you'll find that the weight line is still within the original base of support. So if we were to tilt it this way and we let go, what happens is that this object is going to tilt back to its original supporting base. For the third diagram, if we can tilt it in such a way that's able to balance right at the edge here, this is where we can get the unstable equilibrium. So if you're really good at this, it could possibly remain upright, balancing on the edge like this, and doesn't fall back to the original position, nor does it fall over. And for the final diagram, if this is where our center of gravity is, you'll find now that the weight line is outside the original base of support. So it's going to fall over on this new surface this time. So I've got some students who say, hey, it is still stable, right? It's just that it's found a new base of support. Well, yes, but it kind of depends on which one you consider your base of support. So when we talk about tilting and toppling, the toppling here means that it falls to the new surface. Normally, in order to study toppling, we would be supporting the original base, put it on a ramp, and then we'll tilt it. So if this were to happen, and while it's resting on a surface, it's going to fall away from that ramp. And this can be quite dangerous when you're looking at vehicles. So now let's take a closer look at how the factors we mentioned earlier can affect tilting and toppling. First of all, let's compare base areas. So we know to prevent the object from toppling, the line of gravity needs to stay within the original base area. Let's try rotating the objects. So I'm going to rotate the triangle on the left first. And as you can see, in order to make the triangle topple, it needs to shift until roughly about here. If it goes beyond, this is where it will topple. So this would be the maximum point where it will remain stable. So I'm just going to reposition the weight line to make sure that it makes sense. So that's the maximum angle of tilt. For the triangle on the right, which has a wider base area, let's try tilting it now. And you can see that we can tilt it to quite a high angle. In fact, the weight line has shifted. So I'm going to reposition the weight line, and we can keep tilting it. And you can see from this original position to here, and from the original position to here, because the base area is so much wider, it's a very high angle of tilting before the object will finally topple over. That's why a larger base area is more stable. Just to make a quick visual comparison, let's say this gray line represents the original horizontal position of the base. This would be the angle of tilt. Whereas for the larger base area, this is the original horizontal position of the base, and this would be the angle of tilt it can go up to before toppling. Now let's compare the height of the center of gravity. So now we've got two triangles with the same base area, but one is taller than the other. If we compare the height of the center of gravity, again, let's try tilting both triangles. So this triangle on the left, we need to tilt it, and you can see that as we tilt it, the center of gravity has actually shifted. So I'm going to reposition the weight line to make it more accurate. and this would be roughly the greatest angle which it can tilt to before toppling over. Let's now tilt the triangle on the right. So again, the center of gravity has shifted, so I'm just going to reposition the weight line, and this would be roughly the highest angle it can tilt to before it topples over. As you can see, the shorter triangle can be tilted to a greater angle compared to the taller triangle. Again, let's compare the angles from the horizontal position. I'm putting two lines here to represent the original horizontal positions. You can see that the angle for the shorter triangle, or rather the triangle with the shorter center of gravity, has a greater angle of tilt compared to the triangle with the taller center of gravity. I do have a video where I show a simple activity you can do in order to study tilting and toppling. I've also shared the link in the description below. So why is it important to understand stability? Understanding stability in terms of base areas and the heights of the center of gravities, we're able to understand how to make vehicles a lot more stable. So for example, if we're to look at buses. So on the left here, we've got a diagram of a school bus, and this black arrow represents the weight acting from the center of gravity of the school bus. Is it possible for the bus to tilt? Yes, if it's going up on a slope. As long as the weight line is within the base of support, where this base is supported by the road, then the bus is not going to topple over. However, if the bus is on an incline in such a way that the weight line goes beyond the base of support, then yes, it's possible for the school bus to fall over, and that's not what we want. This is not the new base area that we want for the bus. So when we compare different vehicles like cars and buses, now you should be able to see why the height of the center of gravity is an important consideration to make sure that the vehicle doesn't topple over. Because the car is so much shorter, it would take this much for it to be able to topple over. Whereas for a school bus, the center of gravity is higher, so it also takes this much for it to topple over. However, for a double-decker bus, because the center of gravity is higher, it doesn't take much for it to topple over. So that's why for double-decker buses, if you've ever ridden on one, you'll find that there is a limit to the number of people that can be on the upper deck. Because the more people that go on the upper deck, the higher the center of gravity would be, because there's more weight upstairs. So the more weight we have downstairs, the safer it would be. If the center of gravity had been shifted upwards, let's just reset this, and let's say the center of gravity has shifted upwards, it takes only this much for the bus to topple. So that's why double-decker buses have certain limitations in terms of the number of passengers it can carry, the number of people that can be upstairs, and even what kind of inclines it can go up. That means what kind of slopes it can go up. So you may or may not have read about tragedies where buses have fallen down inclines because they have toppled over. And this is everything to do with the position of the center of gravity relative to the base of support. And this is why physics knowledge is such an important thing in order to prevent tragedies like this. And that is it for this video. So if you found this video to be educational and helpful, please click like and do subscribe for more free physics lessons. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. Do check out my YouTube channel for videos on other lessons which you might find very helpful. To get access to notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Happy studying!